Good afternoon, everyone. Welcome to the week 12 of this course, Principles of Communication System. So, today we are going to discuss some of the questions based on the topic which is covered in the week 12. So, topics like additive noise, white Gaussian noise, and then power spectral density, wide sense stationary. We have already solved lots of questions based on wide sense stationary in the last lecture. So, coming to the first question. So the first question is, consider xt to be a white Gaussian noise with zero mean. Its correlation function Rxx tau is of the form. So xt is a white Gaussian noise with zero mean. So correlation function will be eta by 2 del tau. And then power spectral density will be n by 2. So it will be constant like a light. So this is a constant power spectral density of this. So which is the correct option for this question? Option number A. So now coming to the question number 2. So a real wide sense stationary random process xt must satisfy. So the mean should be constant. Also e of x squared t should be constant and the covariance xt and xt plus tau should depends only on the shift of tau. So all of these options are correct. So option D is correct for this question. Now coming to the third question, consider the probability density function of the message sample M given as, so Fm is given as 3 by 2, 1 minus m squared for the value of m 0 to 1. What is the optimal quantization level corresponding to the interval 0 to 1? So the quantization level will be integration from 0 to 1, 3 by 2 m 1 minus m squared dm divided by integration from 0 to 1, 3 by 2, 1 minus m squared dm. So now when you do this integration, so the numerator part will get 3 by 2 m minus m cube dm divided by 3 by 2 1 minus m squared dm. So now this integration will be, this 3 by 2 and 3 by 2 will get cancelled. So we will get m square by 2 minus m to the power of 4 by 4, 0 to 1. And here m minus m cube by 3, 0 to 1. The value is 1 by 2 minus 1 by 4. And when you put m is equal to 0, the other term will be 0. Here 1 minus 1 by 3. So the values are 4, 2 minus 1 divided by 3, 3 minus 1. 1 by 4, 2 by 3. The correct answer for this question is 3 by 8. So option D is the correct answer for this question. So this video is also recorded and will be uploaded on the YouTube, and the link will be provided in the tutorial session, like in the NPTEL portal. So from there you can access this video. So coming to the question number 4, consider a binary symmetric channel with probability of A naught is equal to 0.6, probability of B1 such that A naught has occurred is equal to probability of B naught such that A1 has occurred is 0.25. AI and BI denotes the events corresponding to transmitted and received signal 0, 1 at the transmitter and receiver respectively. Then find probability of A naught such that B1 has occurred. So first try to understand what is binary symmetric channel. So A naught A1 here, B naught B1. So probability of B1 such that A naught has occurred is this, that is 0.25, and probability of A1 B naught such that A1 has occurred is also 0.25. Okay. So now what is the probability of A naught is given 0.6. So probability of A1, what it will be? It will be 1 minus probability of A naught. So this will be 0.4. Okay. Now probability of B naught such that A naught has occurred, that is equal to 1 minus probability of B1 such that A naught has occurred. So this probability is 0.75. Now the another one, probability of B1 such that A1 has occurred is equal to 1 minus probability of B1 such that, probability of A1 such that B naught has occurred. So this is 0.75 again. So these are the probabilities. Now we have to find probability of B naught such that A1 has occurred. So for this we can write probability of B1 such that A naught has occurred into probability of A naught. Sorry, in this question it is asking probability of A naught such that B1 has occurred. So probability of B1 that A naught has occurred into probability of A naught divided by probability of B1 such that A naught has occurred into probability of A naught plus probability of B1 such that A1 has occurred into probability of A1. So here we will add one extra page. So now we have all these probability values. So probability of B1 such that A0 has occurred is 0.25 and probability of A0 is 0.6 divided by 0.25 into 0.6 plus probability of B1 such that A1 has occurred is 0.75 into 0.4. So this value is 0.15 divided by 0.15 plus 0.3. So this will be 0.15 by 0.45. The final value is 1 by 3. So any option is there? 1 by 3? Yes. Option A is 1 by 3. So the a priori probability A naught such that B1 has occurred is 1 by 3. So done with question number 4. So now consider xt to be white Gaussian noise with zero mean and autocorrelation function for del tau. It is passed through LTI system whose impulse response ht is equal to sine 2 pi t. What is the power of the output random process yt? So when xt is passed through a LTI system, then output is yt. So the input power spectral density is x of f and output power density of sy of f. And the frequency response of ht is h of f. So that is the frequency response of LTI system. So here Syy of f, that is equal to xxx of f into magnitude of hf square. Okay. So now we'll solve this question based on this. And this is the output PST. Now the Fourier transform here ht is given as sine of 2 pi t divided by pi t. So the Fourier transform hf will be like this is equal to 2 of sinc of 2t. So for this, we know what will be the hf. So hf will be just the plot from -1 to 1. So this will be the frequency response of this ht. So here now h of f square, that will be again it will be 1 from minus f to f. So given input is white noise with autocorrelation. Here input is given white Gaussian noise with 0 mean and autocorrelation of 4 del tau. So input is white noise with auto correlation 4 del tau. So which is implied the power spectral density, like that is xsxf is 4. Okay, for all f. So this is, let's suppose, input, that is 4 del of t. So the power spectral density will be 4. So now this value will be 4 into and hf is 1. And for frequency -1 to 1. So this will be equal to 4. So the final value, we'll take the another page. This is equal to, this is our HF mod of HF square, and x-axis is 4. So our power spectral density of output is 4 from the value of -1 to 1. So the correct answer of this question is 4. Sorry, it is asking what is the power of the output signal. So the power is area under the curve of the power spectral density curve. So this area is the power. So area is equal to 4 into 1 minus of -1. So this is equal to 4 into 2. So that is 8. So power is equal to 8. So the correct answer for this question is option number D. So now we'll move on to the next question. Consider Xt to be a white Gaussian noise with zero mean and its power spectral density Sxxf is of the form. So this will be of the form of n by 2. So the power spectral density of white noise is constant. So option D is the correct answer for this question. Consider random variable theta, let's take it theta, uniform is 0 to pi by 2. The probability density function of the random variable phi is equal to tan theta is. So the probability distribution density function is equal to 2 by pi c. This is from 0 to pi by 2. So that is equal to the value will be 1 by pi by 2 minus 0. So that is equal to 2 by pi. So this is the like theta is uniform from 0 to pi by 2. The value is 2 by pi. So that is d tan theta by d theta. So that is equal to 2 by pi sec square theta. So that is equal to 1 plus tan square theta. So tan square theta is pi square. So this is the value of probability density function, that is 2 by pi 1 by 1 plus phi square for the value of phi from 0 to infinite. Coming to the question number 8, consider a wide sense stationary random process xt with power spectral density Sxxf given as input to an LTI system with the frequency response hf. The power spectral density of the output is. So we know that power density, spectral density at the output is Xxf into mod hf square. So the correct answer is option number C. Random process xt is Gaussian if the probability density function xt for any time t is Gaussian, the autocorrelation of the random process is Gaussian. So these two options are wrong. The joint probability density function of xt1, xt2 up to xtn for any t1, t2, tn and any n is for any n is Gaussian. Yes, option C is the correct. The power spectral density of random process is flat over the entire frequency range. So this is wrong. Coming to question number 10. Consider wide sense stationary random process xt with autocorrelation function rfx tau given as input to LTI system with impulse response h tau. So the autocorrelation of the output is, so autocorrelation of the output is Rxx tau convolution with h tau, convolution is h of minus tau, as we have studied in the lecture. So option B is the correct answer for this question. So now we'll solve one question from the lecture series. The question is, consider a wireless signal xt with autocorrelation Rxx tau. So Rxx tau is equal to 1 by 2a e to the power of minus a tau. Okay. So the plot is given as like this. And this value is 1 by 2. So now, what is the power what is the PSD, power spectral density, and calculate bandwidth required when bandwidth required which contains 90% of the signal power. So we'll solve this question. The first question is asking what is the power. So we know that power is given as x square, expectation of x square of t. So that is equal to Rxx 0. So autocorrelation value at 0 is the power. So when you substitute, that is 1 by 2a. So this is the power. Power of xt, that is equal to 1 by 2. Now we have to find power spectral density. So that is Sxxf, that is equal to integration of autocorrelation function. Like Sxxf is the Fourier transform of autocorrelation function, that is integration of Rx tau e to the power of minus j 2 pi f tau d tau. Okay. So this is equal to Rx tau is 1 by 2a e to the power of minus a tau e to the power minus j 2 pi f tau d tau. So this can be given as 1 by 2a 0 to infinite e to the power of minus a tau e to the power minus j 2 pi f tau plus 1 by 2a minus infinite to 0. Here it will become e to the power of minus a into minus tau. So that will be plus tau e to the power minus j 2 pi f tau d tau. So this is equal to 1 by 2a. The integration is minus e to the power of minus a plus j 2 pi f tau divided by a plus j 2 pi f. And the value of tau is 0 to infinite plus 1 by 2a e to the power of a minus j 2 pi f tau, and denominator will be a minus j 2 pi f, and this value is also from 0 to infinite. So now after substituting all the values 1 by 2a, when we substitute tau is equal to infinite, this term will become 0. When we substitute 0, that will be plus 1 by a plus j 2 pi f plus 1 by a minus j of 2 pi f. So this is equal to 1 by 2a squared plus 4 pi squared f squared, and this will be a minus j 2 pi f plus a plus j 2 pi f. So this term will get cancelled. So the answer will be 1 by 2a divided by a squared plus 4 pi squared f squared. So this will get cancelled. So finally we will get 1 by a squared plus 4 pi squared f squared. So this is the power spectral density. 1 by a squared plus 4 pi squared f squared. Now the plot for this will be something like this, and at value 0 it will be 1 by a squared. So the 90% of the power will be from minus omega to omega. Okay, so what is it asking in the question? It is asking calculate bandwidth required which contains 90% of the signal power. So energy of xt in minus omega to omega, that is equal to 90% of the total. So 90 by 100 into 1 by 2a, and that is equal to integration of power spectral density from minus omega to omega. Okay, so now we have to find omega. So this value is equal to 0.9 by 2. So 0. So this value is equal to this is integration of power spectral density. So here we can write x-axis 1 by a squared plus 4 pi squared f squared integration with respect to ds. Okay, and the limit is from minus omega to omega, and this value is 0.9 by 2a. So now when we take 1 by 4 pi squared common, we will get 1 by f squared plus a squared by 4 pi squared df, and this is equal to 0.9 by 2a. So is imply that 1 by 4 pi a square, this integration will be 2 pi by a tan inverse f by a by 2 pi. And the value of f is from minus omega to omega. Now substituting value omega and minus omega, we will get tan inverse omega by a by 2 pi and tan inverse that will become 2. 2 tan inverse 2 pi omega by a. So here this 4 is getting cancelled. So this is imply that 1 by pi a tan inverse 2 pi omega by a is equal to 0.9 by 2. Is imply that 2 pi omega by a is equal to tan 0.9 pi by 2. So that is equal to 6.3138. So now the value of omega is equal to a by 2 pi into 6.3138. So that is equal to 1.0058. So the bandwidth is from minus omega to omega. So this is equal to minus 1.00582 plus 1.0058. And the value of A is equal to 5 kilohertz. So bandwidth is nearly equal to minus 5 kilohertz to 5 kilohertz. So this was the complete solution for this question. So today we will end the lecture here only. So if you have any doubt, you can ask questions in the YouTube in the comment box. Thank you everyone for attending today's session. So I will also take one extra session in the next week that will be informed by the mail through NPTEL. Thank you everyone. Bye bye.